Hi, welcome back. Today we're starting our Chapter 9, Testing Claims About Proportion. In Chapter 8, we talked a lot about confidence intervals, and now we're going to go into testing claims and hypothesis testing. So in this section, it's all about the basics and the vocabulary associated with significance test. Our learning targets for this section is to state the appropriate hypotheses for a significance test about a population parameter, interpret a p-value in context, and make an appropriate conclusions for a significance test. We're going to start with stating the hypothesis. So in confidence intervals are one of the two most common methods of statistical inference. The second most common method of inference is called a significance test, which allows us to weigh the evidence in favor of or against a particular claim. As we start talking about significance tests, one great example that we'll be able to relate to is jury verdict of guilty or not guilty, and we'll talk about it more in class. So a significance test or a hypothesis test is a formal procedure for using observed data to decide between two competing claims called the hypotheses. The claims are usually statements about parameter. Make sure that when we're talking about significance tests, you're talking about the right thing. When we're writing down, we use the correct statistical symbols. The claim that we weigh evidence against is a significance test. It's called a null hypothesis. The claim we're trying to find evidence for is the alternative hypothesis. So relating this back to the jury verdict, proving that someone is innocent, the null hypothesis would be the person is not guilty, and the alternative is that they are guilty. So let's try to do a problem here. A free throw shooter claims that his long run proportion of made free throws is P is equal to 0.8, but we suspect that the player is exaggerating. So here we are going to use our null hypothesis to be P is equal to 0.8 versus our alternative. Since we say he's exaggerating, that means that the p-value, our alternative, would be less than 0.8. And usually the null hypothesis is a statement of no difference. So what he's claiming is that he's 0.8. That's going to be our null hypothesis. And then we're going to try to see the alternative if we have convincing evidence or not against it. So the alternative hypothesis is one-sided if the statements that a parameter is greater than the null, or if the statements that the parameter is less than the null. So for example, in the previous example, that was one-sided. So for example, this is how they would look. So the null could be equal to P is equal to 0.80, and the alternative would be P is less than 0.8, which that means that he was exaggerating, or that he actually is greater than an 80% free throw shooter. So that would be a one-sided. Now, the alternative hypothesis, if it's two-sided, if it states that the parameter is different from the null value. It could either be greater or less than. So the way it would look would be that it does not equal to 0.8, meaning he could either be a better free throw shooter or he's exaggerating. So let's look at this problem and see if we can come up with the null and the alternative. So James is a manager at the Hawaii Pineapple Company and is interested in the size of the pineapples grown in the company's field. Last year, the mean weight of the pineapples harvested from one large field was 31 ounces. A different irrigation system was installed in the field after the growing season. James wondered if this change will affect the mean weight of pineapples grown in the field this year. State the appropriate hypothesis for performing a significance test. Be sure to define the parameter of interest. So notice they did not state if the pineapples were larger or smaller. They just wanted to know if there's a difference. So here, Because James wonders if the mean weight of this year's pineapples will be affected, whether it's positively or negatively, by the new irrigation system, the alternative hypothesis is two-sided. So you do want to make sure you identify if it's one-sided or two-sided to make the writing of your null and your alternative hypothesis a lot easier. So here are null hypothesis, and notice that we're using mu because we're talking about the parameter. The mu is equal to 31 ounces. And our alternative, because it's two-sided, to know if there's a difference or not, the mu does not equal to 31 ounces. And of course, we do need to define our parameter. So our parameter here would be the mu is equal to the true mean weight in ounces of all pineapples grown in the field this year. Now, later on, we're going to see how to use these hypothesis testing to make claims, but right now we're just working with setting up the vocabulary of it. Now, caution, the hypothesis should express the belief or suspicions we have before we see the data. Do not look at the data first and then frame the alternative hypothesis. Okay, so the hypothesis always refers to the population and not the sample, because the whole point of it is we are trying to extrapolate this out to the population. So be sure to state that the null and the alternate hypothesis in terms of the population parameter. It is never correct to write a hypothesis about a sample statistic. So you should not use a p-hat or an x-bar. It should either be a p or the mu, for example. Likewise, make sure to include the word population or the word true or all when defining the parameter. So if we're going back to the previous one, notice I stated the true mean. We're talking about the population there. We are now going to talk about capital P value, not to confuse it with lowercase p proportion or p-hat. This is different. The capital P refers to the probability. So the p-value of a test is the probability of getting evidence for the alternative hypothesis, as strong or stronger than the observed evidence when the null hypothesis is true. Now this seems a little confusing, but once we start using the p-value, it will start making a little more sense. Let's look at a problem here, going back to the free throw shooter. A player who claimed to make 80% of his free throws made only p-hat, 32 out of 50, which is 0.64, in a random sample of 50 free throws. Now, do we have convincing evidence that if he is or if he isn't? So if we notice 64.64 is less than 0.80. So we do have some convincing evidence, but we need to use the p-value to fully see if there is or if there's not convincing evidence. So here's a simulation of a person who's 80% free throw shooter, and this is what would happen if we let them shoot 50 shots in a row of 400 sets and plot each of those data. Now notice that the 0.64 is right here, and 0.64 or lower only happened 3 out of 400 times that they ran the simulation. So 3 out of 100 would be what percentage? Now, let's relate this to something we have done before in stats. Remember when we talked about the percentage of an event to happen purely by chance? So the smaller the percentage, the more unlikely the event will happen. So we have to think about what this means in context of this problem. So in other words, how likely is it for an 80% shooter to make 64% or less by chance alone in a random sample of 50 attempts? So it's not very likely, because if we do the math, the p-value, which is 3 out of 400, is equal to 0.0075, which is smaller than 1%, super tiny percentage, and that is called the p-value. Now let's start interpreting some information. Let's look at this problem. It says the National Institute of Health recommends a calcium intake of 1,300 milligrams per day for teenagers. The NIH is concerned that teenagers aren't getting enough calcium on average. Is this true? So researchers decide to perform a test and notice that they state their hypothesis before they do any research. So they say that the mean is equal to 1,300, which that's our null hypothesis. And our alternative hypothesis is our mu is less than 1,300. So this is a one-sided, where mu is a population mean daily calcium intake for teenagers. So they do need to tell me what that mu represents. They ask a random sample of 20 teens to record their food and drink consumptions for one day. The researchers then compute the calcium intake for each teen. So here comes our statistic. Data analysis reveals that X bar is equal to 1,198 milligrams, and our standard deviation is 411 milligrams. Researchers performed a significance test and obtained a p-value of 0.1405. Now they want us to explain what it would mean for the null hypothesis to be true in this setting. So if the null hypothesis is true, so mu is equal to 1,300 milligrams is true, then the mean daily calcium intake in the population of teenagers is the 1,300 milligrams. Now, let's look at what the alternative would be. Here, they want us to now state the evidence for the alternative hypothesis. So the evidence for the alternative is that our statistic, our X bar, is equal to 1,198 is less than 1,300. Now, how do we interpret our p-value? Here they gave us our p-value, which was 0.1405. Assuming that the population mean daily calcium intake for teenagers is 1,300 milligrams, there is a 0.1405 probability of getting a sample mean of 1,198 milligrams or less purely by chance alone in a random sample of 20 teens. Now, let's make a template. Notice that they started with assuming that the null hypothesis was true. So assuming that the null hypothesis was true, there is a p-value probability of getting a sample mean of, here's the X bar, that the average that they got or less purely by chance in a random sample of 20 teens. Now, how are we going to make a conclusion if there is or if there's not convincing evidence? And that's what we're going to look at next. So remember, when interpreting p-values, many students lose credit on the AP Statistics exam because they don't answer in context, or because they leave out the statement that the null hypothesis assumed to be true when calculating the p-value. So it's very important that you start out with assuming that the null was true, give the probability of getting that specific sample with that X bar, with our statistic, or less purely by chance alone in whatever sample size that they're using. So how are we going to make a conclusion? So when making a decision based on the strength of the evidence in favor of the alternative hypothesis and against the null hypothesis as measured by the p-value. So if the observed result is unlikely to occur by chance alone, when the null is true, meaning a small value, we reject the null. So to remember it a little easier, remember the phrase, if the p-value is small, reject the null. So again, the p-value is small, we reject the null. I know it doesn't rhyme, but it's going to stick. And how small, we'll talk about that in a bit. So if the observed result is now not unlikely to occur by chance alone, when the null is true, so in other words, a large p-value, we're going to state that we fail to reject the null. So fail to reject the null hypothesis does not mean that you accept And we'll talk about that in a minute, okay? So we're not accepting it, we're just rejecting it. So how to make a conclusion in a significance test. So if the p-value is small, we're going to reject the null and conclude that there is convincing evidence of the alternative in context. If the p-value is not small, so in other words, it's large, we fail to reject the null and conclude that there is not convincing evidence for the alternative in the context. So again, if the p-value is small, we reject the null. If the p-value is not small, we're going to fail to reject the null. And remember, everything has to be in context. So how small does a p-value have to be for us to reject the null? So remember in chapter 4, we suggested that we use a boundary of 5%, which is a very accepted value for when determining whether a result is statistically significant. But there are times where we want an even smaller or larger boundary value, like 0.01 or 0.10 when drawing a conclusion in a significance test. So we call that a significance level. Alpha is a value that we use as a boundary to determine if an observed value is unlikely to happen by chance alone when the null hypothesis is true. So as an experimenter, you should always state what significance level you're hoping to work with. This should be done, if we think back to our 4-step process, it should be in our first step, the state. So the alpha level should be stated before the data are produced. So how to make a conclusion is in a significance test, the way we're going to write it. So if the p-value is less than or equal to alpha, we're going to say because the p-value of, and we're going to state the p-value is less than or equal to whatever the alpha level, and you're going to state your alpha level, whether it's 0.05, 0.1, 0.01, whatever the alpha level is, that's what you're going to write it. We're going to reject the null because the p-value is small, reject the null. There is convincing evidence for the alternative in context. If the p-value is larger than alpha, we're going to state because the p-value of, state what the p-value is greater than the alpha and state what the alpha is, we fail to reject the null. There is convincing evidence for the alternative in context. I am going to show you later about tricks we can do to change the power of a test or avoid certain types of errors, and some of it includes changing our alpha level. That is what we do to manipulate the data when it doesn't work for our scenario, and we'll talk more about that later on. So let's look at this problem. Going back to our calcium intake problem, that conclusion, what conclusion can we make about an alpha level equaling 0.05? So remember that they stated our alpha level, our p-value here, they told us was 0.1405, and our alpha level is 0.05. Notice that this value is larger than our alpha. Because it is larger, we're going to fail to reject. So there's always two pieces to this. You want to say because the p-value is 0.1405, which is greater than our alpha, which equals 0.05, we fail to reject the null. Then we need to write more in context. We don't have convincing evidence that teens are getting less than 1,300 milligrams of calcium per day on average. So we don't have convincing evidence. You cannot state that there is or anything like that. It's either we do have convincing evidence or we don't. But because the p-value is larger than our alpha, we don't have convincing evidence. And our AP exam tip here would be if you're asked to make a conclusion for a significance test and no significance level is provided, we're going to assume that the alpha level is 0.05 and you do need to state it. Our other exam tip here is that they recommend, like I told you, you need to write 2-sentence structure. The first sentence should give a decision about the null hypothesis. Are we rejecting the null or failing to reject? make sure to state the p-value in comparison to the significance level. Is it greater than, or is it less than or equal to? And the second sentence should provide a statement about whether or not there's convincing evidence for the alternative in context of the problem. So this is 2 sentences that you have to write for this. And then never accept the null or conclude that the null is true. Okay, so we're either stating that we do have convincing evidence or we don't have convincing evidence. So when a researcher plans to draw a conclusion based on a significance level, alpha should be stated before the data are produced. That's another important aspect there. Now we're done with our first learning targets for Chapter 9.